What specific problem does your proposed recursive SFT method address compared to traditional training methods for smaller models?
The proposed recursive supervised fine-tuning SFT method addresses the problem of model collapse and degradation in smaller models, which is often observed in traditional training methods that rely on unfiltered data. Traditional approaches can lead to catastrophic forgetting and hallucination due to the lack of structured data selection, resulting in diminished performance. In contrast, our method employs a think, prune, train framework that utilizes correctness-based pruning to stabilize training and preserve knowledge while enhancing reasoning capabilities. This approach allows smaller models to iteratively refine their reasoning abilities using only self-generated data, avoiding the pitfalls of mode collapse by maintaining output diversity while prioritizing correctness. Ultimately, our method enables smaller models to achieve performance levels comparable to larger models on coding and math benchmarks without the need for extensive external datasets.
How does the proposed method or algorithm work? Illustrate it step by step, detailing each component of the think, prune, train framework.
The proposed method, encapsulated in the think, prune, train TPT framework, operates through a systematic three-step process. First, in the think phase, the model is prompted to generate structured reasoning outputs for given tasks, utilizing a prompting strategy that encourages coherent reasoning. Next, during the prune phase, the generated outputs are filtered for correctness using ground truth correctness filtering, ensuring that only valid solutions are retained. Finally, in the train phase, the model undergoes supervised fine-tuning (SFT) on its own validated solutions, iteratively refining its reasoning capabilities. This process is repeated across multiple rounds, allowing the model to learn from its own correct outputs while maintaining a stable performance across various metrics, such as pass at 1, pass at 2.0, and pass at 5.0. By focusing on correctness-based pruning, the TPT framework effectively enhances the model's reasoning abilities without relying on external datasets or models.
Can you come up with a simple yet illustrative example on the inner workings of the proposed algorithm using a hypothetical reasoning task? Walk through the main algorithm steps with this example.
To illustrate the inner workings of the proposed think, prune, train TPT algorithm, consider a hypothetical reasoning task where the model must solve a simple math problem. What is 7 plus 5? 1. Think. The model generates multiple reasoning traces for the problem, such as 7 plus 5 equals 12 and 7 plus 5 equals 10. Each trace includes the reasoning steps taken to arrive at the answer. 2. Prune. Next, the algorithm applies correctness-based filtering to prune the generated outputs. In this case, it retains only the correct reasoning trace 7 plus 5 equals 12, while discarding the incorrect one. 3. Train. Finally, the model undergoes supervised fine-tuning (SFT) using the pruned correct output. This step reinforces the model's ability to generate accurate solutions for similar tasks in the future. By iterating through these steps, the model can refine its reasoning capabilities, improving its performance on similar math problems over successive rounds of TPT, ultimately leading to enhanced accuracy and reliability in its outputs.
What are the theoretical or practical benefits of using your method over existing methods, particularly in terms of performance on reasoning tasks like GSM 8K and code contests?
The theoretical benefits of our method, particularly the think, prune, train TPT framework, lie in its ability to avoid model collapse while enhancing reasoning capabilities through iterative self-improvement. Practically, our approach demonstrates significant performance gains on reasoning tasks, as evidenced by the Gemma 2B model improving from 41.9% to 57.6% pass at 1 on GSM 8K, and the Gemma 9B model surpassing Llama 3.1 to 70B instruct with an 82% pass at 1. Additionally, our correctness-based pruning strategy stabilizes training, preserving knowledge and preventing catastrophic forgetting, which contrasts with prior methods that often lead to performance degradation. In code contests, we observe a steady improvement in pass at 1 from 0.90% to 1.14% for the Gemma 2B model, showcasing the effectiveness of our method in enhancing accuracy. Overall, our findings indicate that TPT not only improves reasoning performance, but also maintains diversity in outputs, making it a robust alternative to existing methods reliant on larger models or complex reinforcement learning frameworks.
How was your method validated or tested, and what specific metrics did you use to measure performance improvements?
Our method is validated through a series of iterative fine-tuning experiments using the Think, Prune, Train TPT framework, where we assess performance on benchmarks like GSM 8K and code contests. We specifically measure improvements using the Pass at 1, Pass at 2.0, and Pass at 50 metrics, which evaluate the model's ability to generate correct solutions on the first attempt and across multiple attempts respectively. For instance, the GEMMA 2B model's Pass at 1 improved from 41.9% to 57.6% on GSM 8K after 4 iterations, while the GEMMA 9B model reached 82.4% Pass at 1 from 66.4%. Additionally, we ensure that our evaluation maintains strict correctness criteria, requiring answers to match the ground truth exactly, which reinforces the reliability of our performance metrics. The results indicate that our correctness-based pruning strategy effectively stabilizes training and enhances reasoning capabilities without relying on external datasets.
What are the primary limitations or potential drawbacks of your proposed method, especially regarding mode collapse or the quality of self-generated data?
The primary limitations of our proposed method, particularly concerning mode collapse, stem from the tendency of models to prioritize high-confidence solutions, which can lead to a reduction in output diversity. While our results indicate improved correctness, this focus on accuracy may result in a narrower set of high-probability outputs, potentially compromising the exploration of diverse reasoning paths. Additionally, the quality of self-generated data is contingent on the effectiveness of the pruning strategy. Without proper filtering, unpruned data can lead to performance deterioration. Although we observe that correctness-based pruning stabilizes training and enhances reasoning, it may inadvertently limit the model's ability to learn from a broader range of outputs. Thus, while our method effectively improves precision, it risks fostering a homogeneous output distribution, which could be detrimental in tasks requiring creative or varied responses.